Hello and welcome to The Space Above Us. Episode 122, Space Shuttle Flight 50, STS-47. Land of the 15 times a day rising sun. Last time, we explored the tangled tale of STS-46. This ambitious mission was designed from the outset with unexpected outcomes and failure as a distinct possibility. However, that failure came from a far more mundane source than expected. Rather than reeling the TSS satellite out on a 20-kilometer-long tether, the experiment had to be halted after only a few hundred feet due to an out-of-spec structural bolt. Don't worry though, we'll see TSS again in a few missions. The tethered satellite system was the result of an international partnership between the United States and Italy, continuing in a streak of missions focused on international collaboration. Shortly before STS-46 flew, however, significant progress was made on an international collaboration in space that will soon become a central theme of our story. On June 17, 1992, United States President George H.W. Bush and Russian President Boris Yeltsin signed an agreement to fly cooperative missions in space. Cosmonauts would fly on the shuttle, and astronauts would live aboard the Russian space station Mir. For the first time since 1975, Americans and Russians would shake hands in orbit. And not to downplay the accomplishments of the Apollo-Soyuz test project, but this time the missions would be more than a ceremony and a hopeful look to the future. The upcoming Shuttle Mir era would come with its own set of accomplishments, but would also provide a testing bed for living and working together in space on the International Space Station. Simply docking Apollo and Soyuz was an immense achievement all on its own. But in the coming years, the United States and Russia would have to learn how to truly work with each other, day in and day out, decade after decade, all at 17,500 miles per hour. But today we're focusing on yet another international partnership, this time with the island nation of Japan. For this Space Lab mission, NASA is teaming up with the National Space Development Agency of Japan, or NASDA, the predecessor to today's Japanese Aerospace Exploration Agency, or JAXA. And just like how Germany's Space Lab mission became Space Lab D1, the proposed mission was being called Space Lab J, though Japan also called it the first material processing test. It also picked up the nickname Fuwato 92, with Fuwato being the Japanese word for weightlessness. Work on the project actually began before the shuttle even flew, way back in 1979, with an original goal of flying in 1988. But between the natural tendency of aerospace projects to drift to the right on the timeline and the impact of the Challenger accident, Space Lab J would be pushed back by 4 years, which explains the 92 in Fuwato 92. Japan was flying 36 experiments, including 2 joint experiments with the United States, mostly focusing on material science and life science. Adjusting for inflation to 2020, the experiments cost around $80 million, and Japan paid NASA around $89 million to fly them on the shuttle. At a little under $5 million per experiment, and with a Japanese payload specialist flying to keep an eye on them, that's actually a pretty good bargain. We'll learn about some of the experiments filling Space Lab's racks for this mission in a bit, but first let's learn about the crew that will be filling Endeavour's seats. Commanding the flight was our old friend Hoot Gibson. As I mentioned on the previous episode, Gibson was actually slated to command STS-46, but in July of 1990, Gibson was participating in an air race when another pilot collided with him in an attempted pass. The other pilot lost control and was killed, but Hoot was able to safely land. The incident drew attention to Gibson's participation in the banned dangerous event and resulted in his removal from STS-46. It is curious that here he is flying just a month after STS-46, but I think that from a pilot's point of view, the complexity and unknowns of the tether on STS-46 would have been a lot more appealing. As we know, Space Lab missions come with their own share of complexity, but it mostly falls onto the mission specialists and the payload commander. There's not too much fancy flying. But in any case, a shuttle flight is a shuttle flight, and this is his 4th of 5. Joining Hoot Gibson up front was one of only 2 pilot crew members to fly 6 space flights, Kurt Brown. Curtis Brown was born on March 11, 1956 in Elizabethtown, North Carolina. He graduated from the U.S. Air Force Academy with a degree in electrical engineering before heading off to learn how to fly. The Air Force put him in an A-10, you know, that giant machine gun with an airplane wrapped around it, and the A-10 would be his specialty for the duration of his Air Force career. Supporting the A-10, he flew as an instructor pilot, as an instructor in weapons and tactics, and as a test pilot. He was also testing the F-16 in addition to the A-10 when he was selected by NASA in 1987. And as I mentioned, this is his first of 6 flights. Moving back in the flight deck, we find Mission Specialist 1, Mark Lee. We know Lee from his flight on Atlantis for STS-30, where he helped to send the Magellan uncrewed probe off to the planet Venus. Mark is the payload commander for this flight, so he's got a busy few days ahead of him on this, his second of 4 flights. Sitting right in the middle of the flight deck was Mission Specialist 2, J. Apt. We last saw Apt on STS-37, which deployed the Compton Gamma Ray Observatory. When the observatory's high-gain antenna failed to deploy, Apt accompanied Jerry Ross outside on a contingency EVA, where Ross manually deployed the antenna. On this flight, Apt will be serving as part of the orbiter crew, along with Gibson and Brown. Their job will be to keep the orbiter happy and healthy, while the science crew does their thing down in the payload bay. This is Apt's second of 4 flights. Down on the middeck, we find Mission Specialist 3, Jan Davis. Nancy Jan Davis was born on November 1st, 1953 in Cocoa Beach, Florida, just down the road from the Kennedy Space Center, but she grew up in Huntsville, Alabama. Davis earned a bachelor's degree in applied biology and a bachelor's, master's, and PhD in mechanical engineering. She started her career working for Texaco as a petroleum engineer, specializing in tertiary oil recovery. This is the tricky phase where much of the oil from a reservoir has already been extracted and engineers have to get clever to remove the rest. But I guess oil wasn't Davis's thing because just 2 years later she joined the Marshall Space Flight Center as an aerospace engineer, helping to perform structural analysis for the Hubble Space Telescope. Growing up in Huntsville, Davis became friends with rocketry legend Wernher von Braun, and among her personal effects for this flight was von Braun's 1933 pilot's license, borrowed for this mission. Davis explained, quote, "He always wanted to fly in space and never got to. I see it as a way of taking his memory into space." This is Davis's first of 3 flights. Joining Davis on the middeck was Mission Specialist 4, Mae Jemison. Mae Jemison was born on October 17, 1956 in Decatur, Alabama, but grew up in Chicago, Illinois. Jemison earned a bachelor's degree in chemical engineering and an MD from Cornell a few years after that. Jemison has quite the career, combining engineering and medicine to study computer programming, nuclear magnetic resonance spectroscopy, computer magnetic disk production, a hepatitis B vaccine, and rabies. She also served in the Peace Corps as the Area Peace Corps Medical Officer for Sierra Leone and Liberia. On top of all that, she speaks fluent Swahili, Russian, and Japanese in addition to her native English. She was back in the United States working as a general practitioner when NASA came calling in 1985. This is her first and only spaceflight, and with it she marks another notable first, becoming the first woman of color to fly in space. And finally, Payload Specialist 1, Mamoru Mori. Mamoru Mori was born on January 27, 1948 in Yoichi, Hokkaido, the big northern island of Japan. Mori earned a bachelor's and master's degree in chemistry from Hokkaido University before continuing on to pick up a doctorate in the same subject from Flinders University of South Australia. Mori returned to the University of Hokkaido as faculty in the Department of Nuclear Engineering. There, he performed research in a variety of topics, including surface physics and chemistry, high-energy physics, and nuclear fusion. In 1985, he was selected by NASDA, Japanese equivalent of NASA, to fly on the Spacelab J mission. With this flight, Mori becomes the first Japanese person to fly in space as a real crew member. I say that because a few years earlier, a Japanese reporter flew to the Russian space station Mir, but just as a passenger, and that's not really the same thing. This was Mori-san's first of 2 flights. This flight marks an important milestone, the 50th Space Shuttle mission. Big round numbers like this are always nice to celebrate, and the 50th shuttle mission was always destined to get some extra attention. But for the shuttle, it was particularly noteworthy. With STS-47, more shuttle missions have flown after the Challenger accident than before it. I'm not sure this really says anything profound about the state of the program, but I think it is a nice little milestone that's worth noting. If you're curious how far down the road that milestone is, STS-47 marks 37% on the progress bar of the entire 135 mission run of the shuttle program. And actually, in a complete coincidence that I didn't realize until running the numbers just this moment, this mission is almost exactly the halfway point of the flights that are currently planned to be covered on the space above us. When you add up Project Mercury, the X-15, Project Gemini, the Apollo program, Skylab, the Apollo-Soyuz test project, and 135 shuttle missions, you get 169 missions total. And this is number 84, making it 49.7%. So there you go, milestones abound on this episode apparently. STS-47 had a couple of minor postponements due to issues unrelated to the mission, but when launch day arrived there were no scrubs or delays. The forces of entropy tried their best though. During propellant load, dangerously high levels of hydrogen were measured, indicating a leak. The launch team looked over the numbers, estimated that they would be fine by the time launch came around, and kept the count going. And it turns out that they were right. The hydrogen numbers soon fell well into the acceptable range. So, good job. Also good job to the technicians who scrambled into action when a power failure at the Cape Canaveral Air Force Station led to some range safety computers going down. The computers were restored with no delay in the count. And not even two planes wandering into the keep-out zone could hold STS-47 back, since the Air Force, Coast Guard, and NASA security soon dispatched them using giant fly swatters or whatever it is they do with airplanes that wander in front of rocket launches. Despite all of that, right on time on September 12, 1992, at 10:23 a.m., Endeavour rose off of the pad for the second time, and the 50th shuttle mission was underway. The ascent was uneventful, leaving Endeavour in a 300-kilometer high orbit with a relatively high 57-degree inclination. I'm not totally sure what the reason for the 57-degree inclination was, but I will say that the northernmost part of Japan is only about 45 degrees in latitude, so maybe they just wanted to make sure that everybody could wave to their new payload specialist. As is often the case for Spacelab flights, the crew had split up into two shifts in order to allow for around-the-clock operations, maximizing science output. The red shift consisted of payload commander Mark Lee, pilot Kurt Brown, and payload specialist Mamoru Mori. The blue shift consisted of mission specialists Jay Apt, Jan Davis, and Mae Jemison, who celebrated their arrival on orbit by preparing to go to sleep since the first shift went to the red team. As usual, the commander was free to drift between the teams as needed. While the blue team got ready for bed, payload commander Lee began the long task of activating the 7-meter-long laboratory. Lining the walls of Spacelab J were dozens of experiments studying material science and life science. As you might expect at this point, a number of experiments were dedicated to growing large crystals, a favorite pastime of orbiting scientists everywhere. Other experiments studied the behavior of oil droplets, using some of that slick acoustic levitation technology that we've discussed in previous episodes. Another sought to better understand the fluid dynamics of glass by carefully melting a glass ball. To help visualize the flow, the ball had been peppered with tiny gold flakes, which made invisible flows and currents visible. Another experiment studied a type of convection. On Earth, you're likely familiar with convection as the flow of fluids caused by a heat source. For example, the air in a campfire is heated, making it more buoyant, making it rise. As it rises away from the heat source, it cools down and spreads out, falling back down around the edges. Since the air rises out of the campfire, more air is pulled in from the sides to replace it. This behavior explains, among other things, the tapered shape of flames on Earth. But in space, as usual, things are a little bit different. There is no up for the air to go to. This is why if you light a candle in space, you get a weird, dim sphere instead of a bright, tapered flame. The flame is spherical, since there is no up, and it's dim because the familiar convection current does not exist. Turns out, however, that that's not the only type of convection. If you heat a ball of fluid, one of the properties of the fluid that can change is its surface tension. But since you can't perfectly heat the ball all at once, some parts will get hotter than others, and thus have a different surface tension. This difference in surface tension causes a different type of convection, with fluid moving around due to the interaction of these two now slightly different fluids. It's possible that you've seen this effect for yourself. Have you ever noticed the unusual patterns that can become visible if a little water is mixed in with whiskey? Or those streaks that can form on the inside of a glass of wine? That's caused by an interplay of the different surface tensions of alcohol and water. Okay, great. How is this relevant? Well, On Earth, heat-based convection is a far more powerful effect, making it difficult to observe the surface tension-based convection. But if we take away that 1G environment, we can now study this fascinating and potentially pretty useful interplay between different surface tensions on different materials. Neat. Japan was also flying a number of life science experiments. One of them studied the behavior of two koi fish, the colorful Japanese carp. The fish were exposed to light from different directions to see how they would move in a weightless environment. But there was a key difference between the two fish. Before the flight, one of them had its otolith removed. We've heard of otoliths before. They're essentially a gravity-sensing organ. With the otolith removed, the koi wouldn't be able to tell up from down, even on Earth, let alone in space. So I believe the idea here is that by studying their differing movement, scientists could better understand the role of the otolith sensory data in determining the fish's behavior. Armed with such information, scientists might be able to help another creature that can sense gravity and which doesn't always respond well to weightlessness. Astronauts. Payload specialist Mori also became the subject of a few experiments. Among other things, Mori was tasked with tracking a flashing light while sensors monitored the movement of his head and eyes. This was yet another effort from yet another angle at understanding the role of various human senses in microgravity. Maybe scientists could learn that without a sense of gravity, humans moved their heads more and their eyes less, or they only tracked things that were visible, snapping to the new position when the flashing light turned back on. I'm just making those examples up, though, since this mission is just collecting raw data, which would be studied for years before conclusions could be drawn. But it gives you an idea of why these seemingly strange activities were so valuable. Since NASDA didn't use all the experiment slots available in Spacelab, NASA was happy to fill in the rest, bringing 9 experiments for the crew to work on. One experiment continued the long preparations for life aboard a space station. When a mission could extend for months or maybe even a year, the chances that a crew member might need some medicine went up. So one experiment focused on the preparation and use of intravenous medication. Another studied the behavior of frog embryos in weightlessness. And we'll get into more detail about that after I make a dumb joke in a few minutes. You'll love it. In addition to the frog embryos, our old favorite, the lower body negative pressure device, made another appearance. I imagine that the crew were a little more enthusiastic about it this time, since during their long, boring shifts in the device, they were now able to enjoy the view from Spacelab's small window. And just to really build on the international aspect of this mission, there were also a few experiments on the shuttle middeck, including an Israeli experiment studying hornets. I gotta say, I know that the astronauts put a lot of faith in their teams when they climb aboard a 4 million pound vehicle that's mostly made out of explosives. But they must really have faith in their teams to agree to spend a week in space with 180 hornets. That's some real confidence in the team that made the enclosure. The reason that the hornets were included on this flight was that on Earth, these particular hornets rely on their sense of gravity to know which direction to build their nest combs. Experiments and centrifuges on the ground confirm that changing the apparent direction of gravity changed how they built the combs. So what happens if you remove that apparent direction of gravity altogether? It turns out the hornets were not big fans of this. By the end of the experiment, they had failed to build anything, though they may have had other things on their little hornet minds. Despite the best improvised efforts by the crew to fix the situation using some suit fans, the humidity inside the enclosure grew to oppressive levels, a far cry from the nice dry deserts of Israel. By the end of the flight, they hadn't built anything of substance, and 2/3 of them were dead. Yet another reason not to send hornets into space, I guess. Somebody add it to the list. Typically on these Spacelab flights, we see 2 payload specialists. This makes sense because usually payload specialists are scientists who have years of specialized training in running experiments in their particular field of study. But as we've gone over previously, the mission specialists, who are career astronauts, were not wild about this. From their point of view, yes, these payload specialists were indeed world experts in their fields. But the mission specialists weren't exactly slackers. Most of them had extensive science backgrounds, had trained for years to do just about anything in space, and were also just some of the smartest and most capable people around. Plus, they really wanted to fly in space. So surely they could handle the experiments that the payload specialists were being flown for. Well, on this flight, Team Mission Specialist would be able to make their case. Mission Specialist 4, Mae Jemison, in addition to blazing a trail for girls and women of color everywhere, was also blazing a trail for science-minded mission specialists. She was the first science mission specialist. Jemison's job, just like the flight's lone payload specialist, would be to stay laser-focused on the science aspect of the mission. I'm not sure what conclusions were drawn about a mission specialist's ability to perform a payload specialist's job, but considering Dr. Jemison's extensive science background and the bounty of data returned on this flight, it seems to me like she made a pretty compelling case. One interesting aspect of this flight that you will not find in the press kit is that during their training together, mission specialists Mark Lee and Jan Davis fell in love, and shortly before their flight actually got married in secret. NASA had a policy of not allowing married couples to fly together out of concern for throwing off the crew dynamics on a mission. But when Lee and Davis revealed their marriage, it was done so late that the only reasonable option was to allow them to fly anyway. But crew dynamics were not NASA's only concern. Likely on the minds of the public relations folks were exactly the types of questions that came flooding in from the media and the general public. Oh, a married couple flying together? What possibilities could weightlessness add to their, private lives? Get it? You get it? Yeah, we got it. But don't get any funny ideas. The entire crew were professionals. And married or not, their focus was on the mission, not their personal lives. Plus, with 7 people stuffed into a relatively small spacecraft, and with Lee and Davis on separate shifts, there would be few opportunities for alone time anyway. But I know you can't help it. Despite all of the pleading reassurances from the crew and from NASA PR, you're wondering what anyone would wonder. So, I'm happy to report that yes, for the first time ever, this flight did indeed determine that reproduction in vertebrates is possible in a weightless environment. That's right, it's time to get into the details about the frog experiment that I mentioned earlier. Why, what did you think I was talking about? On Flight Day 2, Science Mission Specialist Jemison injected 4 female frogs with a hormone that would prompt them to lay eggs. These eggs were later fertilized with sperm, and their growth was closely observed. The goal here was to answer a centuries-old question about the effects of gravity on the development of complex creatures. A frog egg is separated into 2 halves. One half contains all the cellular machinery to make, a frog, and then the other half contains a bunch of energy-rich material, just like a yolk in a chicken egg. These 2 halves have different densities, so when laid in the water, the heavier half rotates to the bottom, and the lighter half rotates to the top. It's a nice simple mechanism to guarantee that the egg is oriented in a particular direction. I'm no developmental biologist, but from what I understand of this stuff, that's actually a pretty big deal. As an embryo forms, it relies on gradients of certain chemicals to dictate what cells turn into what body parts, and then what chemicals get released next. The whole thing is a carefully balanced ballet of proteins, hormones, and cells, with gravity maybe, or maybe not, playing a big role. Scientists naturally wondered what would happen if something messed with this whole process. Learning how it broke down would tell them more about how it worked. The answer was elusive, though, since these eggs were exceedingly delicate, and messing with them was likely to just damage them. So, on this flight, a number of frog eggs were fertilized, with some being placed in a centrifuge to simulate a normal gravity environment, and some remaining in weightlessness. Throughout the flight, the crew would monitor their development, making observations, taking photos, and occasionally using special chemicals to freeze some embryos in time. That way scientists on the ground could have a sort of frog embryo timeline to study. And to add one more dimension to this, some eggs that had been fertilized and partially grown on the ground were also brought on the flight. The resulting tadpoles swam in weird looping patterns, apparently confused by the weightlessness. Partway through the mission, the eggs that had been fertilized in space also grew into tadpoles. And that's already a pretty remarkable achievement. These complex vertebrates had somehow developed seemingly normally, even without a sense of up or down. Not only that, these tadpoles swam in normal straight lines. Again, I'm no developmental biologist, so I'm not quite sure of all the ramifications of this discovery, but it was a big finding for the field, and it could only be done in space. Plus, again, the real work had only just begun. Scientists would spend years poring over this data, extracting all the knowledge they could from it. Along with all the science experiments on this flight, we also find the space above us favorite, the Shuttle Amateur Radio Experiment, or SAREX. When I see SAREX on the manifest, I get all excited because it means we're in for some pretty cool stories of interactions between the crew and people on the ground. But this time, I've got nothing. The only crew member from this flight who did an oral history was Hoot Gibson, who barely mentioned the mission once in 173 pages of interviews. I still wanted to bring it up, though, to give you a tantalizing little nugget that I found in the mission report. It says, quote, "The SAREX provided communications between the orbiter and the Mission Control Center through an amateur radio station in Brisbane, Australia, during a loss of NASA air-to-ground communications on Revolution 92. I don't know what that's all about, but it sounds to me like SAREX actually fulfilled its ostensible purpose and allowed the crew to maintain communications with Houston even when their primary systems went down. If anyone knows more about this, shoot me an email at jp@thespaceabove.us. Otherwise, it'll just remain a fascinating little almost story. I may not have any oral history stories, but I did find a pretty great quote from payload specialist Maury. In it, he describes how he spent 4 straight hours peering into a microscope, carefully observing kidney cells growing. As he points out, the experiment was really interesting, but the minute-to-minute task of staring through the microscope was not the most thrilling. At the end of his task, with angry muscles and a throbbing headache, Maury moved back from the microscope and stretched, bumping his hand against the window. He glanced out of the window and was captivated by the view of the Earth outside, and how much it resembled the view through his microscope. Maury-san said, quote, "The configuration of Earth below looked remarkably like the living cells I had been examining. There was an extraordinary and indisputable similarity, a repetition of the microscopic and the macroscopic, molecular nature mimicking itself on a gargantuan scale." And that sounds like a pretty magical moment. Even magical moments have to come to an end, though. As is quickly becoming standard procedure, the mission was extended by a day when it became clear that adequate consumable margins were available. But on flight day 8, it was time to come home. The crew packed away the experiments, moving some items to the middeck so that technicians could quickly get them to waiting laboratories. They sealed the Space Lab hatch, dug the mission specialist chairs out of storage, put the bulky orange launch and entry suits back on, strapped in, and the pilot crew did their thing through an uneventful deorbit burn and entry. We've seen the new drag parachute used twice now, but there was a slight tweak in how it was used this time. While they were still gaining confidence in its behavior, the chute was only deployed after both main and nose gear touchdown. Now that they had a pretty good handle on things, the chute would switch to its operational procedure, deploying between main gear touchdown and nose gear touchdown. I believe the idea here is to stabilize the vehicle a bit before bringing down the nose gear, but that's just me speculating based on my understanding of the vehicle. 9 seconds after main gear touchdown, the mortar for the chute fired, and it came streaming out behind Endeavour. Somewhere along the way, it seems to have gone slightly off course, causing some minor heat shield damage. Also, after the nose gear touchdown and the parachute fully inflated, it sort of veered off to the side a bit, imparting a yaw force on the orbiter. But we have multiple redundant systems for a reason, and the nose gear steering was able to take care of the unexpected yaw with no problem. In the end, this was no big deal, just an interesting little tidbit and a nice excuse to talk about the parachute, the flashy new addition to the orbiter. In any case, Endeavour rolled to a stop at the Kennedy Space Center without incident, adding 7 days, 22 hours, 30 minutes, and 22 seconds to Endeavour's growing flight log. The mission was deemed an overwhelming success, returning more data than had even been hoped, and breaking new ground on developmental biology in space. It was also a diplomatic and organizational victory that was the culmination of 13 years of work between the United States and Japan. With Japan providing hundreds of scientists, dozens of experiments, and one lucky payload specialist, all from half a world away, Space Lab J was an accomplishment even before it lifted off. But it did lift off, and it helped to cement a future in space between the two nations. Yoku dekimashita. Next time, Columbia is back on the launch pad, and we'll try to figure out why NASA wants to send a 900-pound disco ball into medium Earth orbit, and then, and this is true, fire lasers at it. Maybe the shuttle was just trying to get back to its 1970s origins. Ad Astra, catch you on the next pass.